we need two further auxiliary results. First, we will get a bound on binning rates. Somehow we consider now the channel coding dual of Slepian-Wolf binning. So if you remember in Slepian-Wolf, it was distributed source coding. We got two sequences, xn and yn, and want to compress them to w and v. Now it's different, the situation is different. In coding, we generate code words xn and yn in the usual manner. And because that for source coding requires that the bins should be small enough so that there is at most one typical xn, yn in each bin. At least we want to have the probability very small, go to 0 if n goes to infinity, that there's more than one typical in each bin. Now we ask the different question: how large must the bins be to be ensured that there's at least one typical x and y in each bin? So here you have your bins. So these are again w1 is the message, and v1 is the size of the bin. So this is a message and this is a bin size somehow. And the probability that there's no typical x and yn in bin w1, w2 is this one here. That's we write it at p sub bin e of w and w2. So that's the probability of the cut that xn, w1, v1 and yn, w2, v2 are not typical concerning x and y. The difficulty in upper bounding is that it involves an intersection of dependent events. That's rather than a union. A common approach of treating this problem is the second moment method of Alone. And we use this model and show that this probability is small if n is large, and the binning rate satisfy that R1 prime plus R2 prime is bigger than the mutual information between x and y. So you see R1 prime is the size somehow of the first bin, R2 prime is the size of the second bin, and if this sum is bigger than the mutual information of x and y, then the bins are big enough. That's the first auxiliary result. The second is again something in the manner of typicality. So we assume that xi is emitted by a discrete memberless source. We have a channel from u to x, and un, yn is jointly typical concerning u and y. Now we want to estimate the probability that xn is in the typical set concerning u, x, y, conditioning that un is equal un. And this is approximately 2 to the minus n times the mutual information of x and y under the condition u. You see this goes to 0, this part goes to 0, and in the lower bound, this part goes to 0, and this part all goes also to 0. You see how one gets the upper bound again. You just write down this probability here as a sum over all typical sequences, and then you can estimate all this by the same probability, and then you count the number of these typical sequences. This is 2 to the n times this time. This probability is estimated by 2 to the n times h of x under the condition u. And if we put these two together, we get exactly what we want. And we get the lower bound with similar steps we used before.